Thanks for joining me as we finish up our last video with ionic formulas. Today we're going to be going through some things called polyatomic ions and go through how to write and name ionic compounds that have polyatomic ions in them. All right, so first of all, this learning objective is pretty similar to all the other ones. The only difference is how do we write and name things that have this thing called polyatomic ions. Our vocabulary is pretty simple today because the only thing that we're adding is polyatomic ions, and we'll hit that on our next slide. All right. So a polyatomic ion is a group of atoms that kind of works as a unit. Earlier we had talked about monatomic. Literally the prefix poly means many. I've seen this in a math class before with polygons. And so effectively it's several different atoms. Like in this case, you've got a nitrogen and 4 hydrogens. They all kind of clump together like a thing of fruit or grapes. But you'll notice that they still have a charge to them. And so then, even though it looks a little bit more confusing, they still behave just like a monoatomic ion. So for example, ammonium that has a plus charge would still behave just like sodium with a plus charge, or this thing called acetate, which is a couple of carbons and a couple of oxygens. It would still behave, and some hydrogens over here too. It would still behave just like a -1. It ends up having a negative charge. Now, there's nothing you can notice to look at this to know what the charge would be. We end up using charts to be able to help us with that. So there's nothing that we have to memorize or to figure out. So you'll notice if I go backwards, the examples still have oxidation numbers, just like we had before, like +1, -1, -2. So effectively, we don't really have to learn how to do anything new. It's just seeing some groups of atoms put together a little bit differently than you're going to have been used to. Okay, so there's some examples we have here. Again, we don't have to memorize these. You should be getting an updated periodic table that has a list of common polyatomic ions on the back of it. When you have these, you'll notice that we've got names, and then it's kind of got the formula of that ion. You'll also notice that there's a charge for each one of them. So some of them are +1, some of them are -1, some of them are -2. You'll notice most of them are minuses, and most of them tend to act like non-metals. There's not very many of them that have a positive charge. There's a couple, but not very many. So let's think about how do we go about naming things? How do we use formulas? So it's possible that you can have 2 polyatomic ions and we stick them together. So all that we really have to do is just find the names of them. So if we have this formula that you're seeing like this, and you're like, whoa, that's kind of weird. Again, we've got a couple of different parts right here. Now, part of it is you have to get used to seeing what is what. You'd have to find it over here in our list, particularly if you have the periodic table, the big list over here. So if it's polyatomic, then it's going to have several things on here. So before, we've just been seeing things like, a nitrogen and a phosphorus together, just a couple of letters from the periodic table. So obviously there's 4 different things right here going on. And so you kind of have to figure out, where am I drawing the line? Is NH4O, is that a thing? Or is H4OH, is that a thing? Or is NH4 a thing and OH is a thing? Like trying to figure out what pieces we have here. So if you come up here and look, you'll notice that NH4 is its own thing called ammonium. And you'll notice that there's an OH, which is its own thing called a hydroxide. So when we figure out where the dividing line is here between the positive and the negative, that's literally our name. We just write down what we see up here. So we've got ammonium, which is the first part. We've got hydroxide, which is the second part. And that's pretty much it. We're done. We don't have to do any other naming. So NH4 is ammonium, OH is hydroxide. And you'll notice, there's no other numbers in here because basically NH4 is a plus, OH is a minus. And so we don't use any parentheses to set them off like you'll see here shortly. Okay. So when we want to give a name, again, we just look it up and we use the name. Here's another example, Ca3PO42. Now this one's a little easier to see because there's some parentheses in here. Sometimes we do use parentheses. We'll use parentheses if there's more than one of them. That would be like we've talked about before, if you had Mg, say Cl2. So in this case, if we had a 2, that would tell me I've got 2 chlorines. Well, in this case, I don't just have two chlorines. Like in this case, I've got 2 of this entire thing in parentheses. So when we use parentheses, this 2 is going to double everything in front of it. This 3 is going to tell me that there's 3 calciums. Now, why would I get a 3 and a 2? If we crisscross, it probably has something to do with the charges. The PO4 would have been a -3, and the calcium is still a +2. But if we were just naming it, it's a little bit simpler. Ca is still calcium. right? So we call this calcium phosphate because Ca is still calcium, and PO4 is phosphate. We get this from the chart, and we're basically done at that point. So we just put the two names together, and that's all that we really have to do. All right, so PO4 again is phosphate. The parentheses, again, we use those if we have more than one of them. In this case, there's two of them, so we end up throwing parentheses around it. If there's only one, we would not use parentheses. All right, so how do we go about writing a formula? If we start with something like calcium nitrate, again, we use the same methods. It's just a little bit more complicated because we got to look something up. All right, so if I'm going to write a formula, calcium is still calcium. I'll look on the periodic table and it's +2. But now this is where looking up nitrate, remember this is not nitride. Nitride would be nitrogen on the periodic table. This is not nitrogen on the periodic table. This is nitrate, which is N3. And so in order to write the formula, then I'm going to use calcium for Ca and I'm going to use NO3 for nitrate. At that point, we just look up the charges on the periodic table like we had done before. We crisscross our charges like we had done before, and we end up getting something like this with CaNO3 too. So calcium would have been +2, which is why we end up with a 2 down here. Nitrate is a -1, which is why we end up with a 1 right here. So again, we just clean this up by getting rid of the 1 and moving on. So again, don't have to do any new rules. We're just using some new words and they still act the same. Another example, sodium carbonate. Again, sodium's on the periodic table. Carbonate is not on the periodic table. So it's going to be polyatomic. We're going to use the chart to be able to figure it out. Sodium is +1. Carbonate, if we come over here and look at it, is a -2 on our chart. And then if we crisscross our charges, we can get everything figured out because, again, sodium would have been +1. Carbonate is -2. So that 2 ends up over here with the sodium. This 1 ends up over here with the carbonate. Now notice there's a 3, but that's still part of the carbonate. So effectively, it's like we have a parentheses around the carbonate, and there's a 1 there. But again, if there's a 1, we don't have to write the 1. And if there's a 1, we don't need to write the parentheses around it. Okay, so no parentheses around the CO3 since there's 1. What if we have a transition metal? Again, this should be pretty easy. Again, chromium 2 would have a charge of +2. Phosphate is not phosphide. So phosphate, we need to come over here on the periodic table, excuse me, our chart, and look at it. We get a PO4, tells us what the charge is there. It's a -3. We can crisscross those. Once we crisscross those, we can get our formula, switch the 2 and the 3 down at the bottom. So effectively, like I said, the chromium started out as a +2, so the 2 ends up over here. The phosphate started out as a -3, so the 3 ends up over there, and that gives us our completed formula. Okay, what if we have two polyatomics? Well, again, we don't do anything differently. We just have to write everything out. So ammonium sulfite, both of these are polyatomics. Ammonium is up here, it's NH4, has a +1 charge. Sulfite is over here, has a -2 charge. We write everything out. We crisscross our charges. If we crisscross our charges, the NH4, which would have been a +1, ends up over here. So we don't have to write anything. Sulfite's a -2. And that 2 ends up over here. So again, not doing anything new other than having a few names here. What if we have a transition metal and it's polyatomic? Because remember, we have to figure out which version of copper it is. So we can work everything backwards. Let's reverse crisscross, right? So if I can figure out what copper's oxidation value is, I can figure out what needs to go in here. So if I've got a 2 here and copper's got an invisible 1, if I reverse crisscross, that gives me a -1 up here for the nitrate. That gives me a +2 over here for the copper. And then I want to double check, does nitrate have a +1? I mean a -1? Nitrate does have a -1. If my nitrate has a -1, then copper must be a +2. So that would tell me that I need to be able to put the Roman numeral 2 in there for copper. So again, we don't have to do anything different. We just have to recognize that nitrate is not something that's on the periodic table. So again, our rules are no different. Polyatomics are just a group of atoms that work together. They basically still follow the same rules that the monoatomic things that we have done so far. It just gives us one more thing that we have to think about as we're going through and writing the names and the formulas. We have to pay attention to things being on the periodic table. The key thing to remember is that if it ends in an IDE, that means that's when it's going to be on the periodic table. If it's not ending in an IDE, it's most likely a polyatomic, and we need to check out the periodic, our extra chart for that. And again, we will use parentheses around the polyatomics if we end up with more than one of them. If we only have one of them, we don't use the parentheses. So hope the practice goes well. Thanks for joining me.